Hi, my project aims to determine a way to repurpose the byproducts of Friedel reactions as water treatments to reduce waste production in industrial synthesis. The idea here is to find a way to repurpose the aluminum hydroxide and hydrogen chloride gas byproducts produced in Friedel reactions in order to reduce their impact on the environment, specifically through testing their potential as flocculants for water waste treatment. The early stages of synthesis of many of our everyday objects, fabrics, cosmetics, even things like pharmaceuticals and plastics, utilize Friedel-Crafts reactions. This reaction in chemical synthesis essentially works to attach an alkyl or acyl group to an aromatic ring, commonly benzene as shown in these models, and this process is fundamental in the production of a variety of aromatic compounds necessary to create these everyday products, these fabrics, cosmetics, plastics, pharmaceuticals. Now, these reactions utilize Lewis acids as catalysts. The problem here with this process is that catalyst, or specifically aluminum chloride as a catalyst. A traditional catalyst enters a reaction, speeds it up, and leaves unchanged. A Lewis acid catalyst within Friedel-Crafts reactions functions differently by not only speeding up the reaction, but binding to the final product and creating a stable complex that must be broken down in order to obtain just the intended product. Breaking down this complex generates byproducts in multiple forms. In the case of aluminum chloride, which is widely used as a catalyst due to its low cost, availability, and reactive versatility, these byproducts are in the form of toxic waste, often more massive than the intended product itself. Specifically, this means sludge composed mostly of aluminum hydroxide as well as hydrogen chloride gas, which are both extremely hazardous and corrosive. And proper disposal of these byproducts is very expensive, thus they often end up in landfills where they leach into surrounding environments and can disrupt entire ecosystems through direct toxicity and acidification. So is there a way to reduce the environmental impact of these byproducts? Currently, the sequence of coagulation and flocculation is prevalent in industrial water filtration. Coagulation functions to destabilize suspended particles, and flocculation collects them into clumps for easier removal. Commercially, some of the most common materials used in this process are alum, or potassium aluminum sulfate, and PaC, or polyaluminum chlorides, which are both notably aluminum compounds, effective because of the charged aluminum ions that they release. This then raised the question, can the aluminum hydroxide byproducts be used in water treatment, effectively not only reducing waste and therefore the environmental impact of industrial chemical synthesis, but also working to streamline water filtration? So of course, I hypothesized that if these aluminum hydroxide and hydrogen chloride byproducts are used in water treatment, then they will be effective in aggregating intended waste. This investigation is divided into two main processes: synthesis of the byproducts and their use in water waste aggregation. Before the byproducts can be tested for flocculation ability, they must be synthesized. So to do this, two small-scale reactions were completed to model industrial manufacturing. First, the alkylation of tert-butylbenzene from tert-butylchloride and benzene, and second, the acylation of 4-methoxyacetophenone from anisole dichloromethane and acetyl chloride, which both were catalyzed by aluminum chloride and serve as key examples of fundamental Friedel-Crafts reactions in chemical synthesis. Think the reactions necessary for items like ibuprofen. After synthesis, in order to store and later use the byproducts of these reactions, hydrogen chloride gas was trapped in water as hydrochloric acid, and aluminum hydroxide compounds were filtered and isolated as much as possible. The idea is essentially testing aluminum hydroxide for its efficacy as a flocculant and testing hydrogen chloride gas for its efficacy as a flocculation aid, or if its presence can improve efficiency. This was done by suspending calcium bentonite clay in water and adding aluminum hydroxide byproducts, then comparing the clumping of the clay to that within groups given alum, the commercial flocculant. Two aspects were changed between groups to optimize results: the pH of the byproducts and the pH of the water, which was changed through the addition of hydrochloric acid byproduct. So this means the independent variables are the aluminum hydroxide and the hydrochloric acid, while the dependent variables are the area and color of aggregated clay, as well as the color of surrounding water. These results were then compared to the positive control, alum, and the negative control, no treatment. The hypothesis was in fact supported. Looking at this photograph, the difference between clay aggregation in treated and untreated groups is visually evident. When compared to the dense circular clumps in the alum groups and the dispersed clay in the untreated groups, aluminum hydroxide groups demonstrate apparently successful aggregation. To determine which factors were ultimately the optimal treatment, three aspects, the dependent variables, were considered: the area of the aggregated clay mass indicating how tightly the clay was collected, the color of the mass indicating its density, and the color of surrounding water indicating the presence of unaggregated clay. Overall, aluminum hydroxide and hydrogen chloride byproducts of Friedel-Crafts reactions are in fact effective in flocculating waste, with aluminum hydroxide at a pH of 3 and water at a pH of 5 being the most effective. By identifying an effective way to repurpose hazardous byproducts of chemical synthesis as water filtering agents, this project presents a cost-effective way to reduce environmental degradation worldwide. Thank you.